And then finally, I'll give you a little bit of teaser to show you how we can sort of ground all of these directly into our robotic policies and how maybe we could think about applying these better improved VLMs to redesign VLAs. Okay, so let's get started. We're going to start out by talking about Blink. Okay, so we know that these models are really good for a wide variety of tasks, right? You can ask it to sort of describe an image, and it'll give you these descriptions that are really, really good. It does a generally good job of identifying objects, but then when you ask it something as simple as, can you identify or 3D space, and you can ask about 3D space in a variety of different ways. We've released a bunch of benchmarks to try to do this. An example of trying to probe for 3D understanding would be something like, is the camera moving to the left or to the right, going from photo A to photo B? And people are pretty good at this. They'll tell you that the camera is moving to the left, but GPT gives you the wrong answer, and Gemini just completely gives up. The same thing can be applied to a variety of other kind of localization tasks as well that require more sort of fine-grained understanding of what's in the image. So here we're trying to ask what is a better bounding box for the pizza. And again, people will tell you that A is the better bounding box. This is not a hard task at all. But again, all of these proprietary VLMs, they just can't seem to be able to answer these questions. Now, of course, these might look like anecdotal examples to you, but we found systematically that these things hold true even today. Here's another even simpler task where we ask the model, what's the best image that fits in this missing part? And again, people are pretty good at this. They'll tell you that obviously that sign, that banner needs to be completed. So A is the correct answer. But again, all these models completely fail to even answer this simpler question. So what fundamental capabilities do we really care about, right? So I'm giving you some examples, but ideally we want to have something that's a bit more systematic, something that tells you, okay, here are the core capabilities that we must have in our VLMs. The nice thing is the CVPR community, the sort of computer vision community, they've been thinking about this for a really, really long time, for decades in fact. So there are very core problems that have been defined by all of the researchers we have in our community. Things like semantic affordance. This is a core task in computer vision. So identifying which point is most similar in affordance, or something like multi-view reasoning, which direction is the camera moving, or something like visual similarity, which two images are the most similar out of this group. You can also think about localization, which is an example I gave you, in painting, which is another example. We can also ask about depth, which point is closer to you. There's also color. If two points are the same color or if one point is darker, this is again something that's core to understanding vision. And then of course there's forensics, right? Can you make sense of whether an image is generated or real? These are core tasks that our community has tons of different workshops going on across the day today, just exploring different aspects of these different components. But let's take a step back and look at what are our benchmarks evaluating our VLMs for. They're evaluating our VLMs on their ability to forecast what's going to happen next, on social relationships, which can be subjective, on geolocation, whether it can identify where a picture was taken, and sometimes on recognition, which is good because recognition is one of those core capabilities, but it's only a small part. And then sometimes it asks about music theory or things that require external knowledge, which is not really perceptual information, but seems to conflate perception with a lot of general knowledge or reasoning. Right? So there's a bunch of different things that we're actually evaluating our models for, and we seemingly have forgotten all these core perceptual capabilities that we should be evaluating our VLMs on. And so noticing this, we developed the Blink benchmark. And the Blink benchmark is really a benchmark that's aimed at evaluating these classical notions of what it means to see and perceive the world. So it contains these tasks, but repurpose those tasks in a visual question answering format so that we can evaluate VLMs for those tasks. So we can ask things like visual correspondence tasks, which points are the same. We can also ask semantic correspondence tasks, which point A, B, C, or D is most similar to 1. And again, this is the left paw of the cat, so it should be obvious that the correct answer is C. We also can test for IQ, so reasoning about 3D shapes and how we can put them together to solve different kinds of tasks. We can ask about relative reflectance. We can also ask about relative depth and a variety of other kinds of tasks. So the benchmark overall contains about 7,000 different images and a bunch of different multiple choice questions across these 14 core vision tasks that we've identified as core problems that the vision community cares about. Some of these tasks are low level, some of them require high level vision, some of them require mid level, some of them require pixel level perfection, some of them just require high level sort of image understanding. So we've divided the entire benchmark up into different components, depending on the different applications that you might care about. So let's take a look at some of the results, because it's always fun to sort of see where we are. Humans are very good at this. So random chance is about 38% on this bench, which is really good, right? Because these are tasks that are very easy. These are very core capabilities that we're all really good at. So let's take a look at some of the open weight models that are out there. All these open weight models perform about random chance on these tasks. That's a really bad sign. And then when you look at the closed source models, most of them, again, barely go above random chance. The only exception being GPT. GPT-4, Turbo, and 4.0, those are the only ones that move the needle at all beyond random chance. And the best performing model that we had when we evaluated these earlier in 2024 was at about 60%. Since then, of course, they've incorporated a lot of this data set. These numbers don't really hold anymore. But you can look at the older versions of models and they don't. Yeah. You can also create this data set yourself and see if these models perform better, and turns out they don't. So we also know that these companies are essentially just taking all of this data that we're creating and training.
Testing Zoom, 1, 2, 3.
So are these tasks too difficult to solve? The answer is no. They're not too difficult to solve. Even the machine learning community or computer vision community has created a lot of specialist models that are very good at this task, that achieve human level performance. So models like DIFT or Depth Anything or a variety of other kinds of models, they perform at about 90%, or if not 90, at least 70% on these tasks, way higher than these generalist models that we want to be using. So there's this big gap, right? Big gap that's sort of left behind, where our VLMs just are unable to see, unable to do these core tasks that we know as a computer vision community that we can 100% solve, right? So that's where the field is. What's exciting about this benchmark is that unlike other benchmarks like MMBench or MMMU, which are typically the ones that people use to evaluate VLMs, if you just convert the vision part into language, all the performance numbers improve. But for Blink, you can't convert things into language because it's a core vision capability. And so converting to vision, language doesn't help you solve the task. You need vision to work well to get this model to answer these questions, right? So this is what makes Blink very different from all of these benchmarks that are out there. And if you look at another visualization of these same sort of results, human performance really is really, really good. And all of our models are much, much worse at being able to do this task. So there's a long way to go. So how do we go about evaluating and improving these kinds of models? Let me show you an idea called sketching that I've been really excited about for the last year or so. So the idea I want to sort of demonstrate by taking you back to your middle school days. So if I were to give you this question, this geometry question, which for those of you who took any math course or geometry course should be able to solve, if I asked you what is the angle EIC, and I gave you a couple of other angles, there are things that you can do to make this problem a little bit easier. And the thing that you should have learned from your geometry course is that you can sketch out this really nice line that goes through here. And then as soon as you do that, all of these intermediate angles become really easy to compute. And because you can compute those angles, now you can answer the question and tell me that EIC is just 150 degrees, right? So this idea of sketching is fundamental. It's something that you learn very early on to be able to solve tasks. Let's try another question. So here's an example of a question. Let me ask you this question, actually. Is f of x a convex function? Who thinks it's a yes? It's a little bit hard. Yeah, maybe. There's some people. Who thinks it's a no? It's still hard. It's okay if you don't want to answer. Okay, some people again. What if I drew it for you? What if I sketched out the function? Who now thinks it's a convex function? So a lot more people think so, right? So this idea of sketching is fundamental. It helps you solve tasks a lot better. It's something that Barbara Tversky has spent her entire life advocating for and solving. And if you haven't read her book, Mind in Motion, I really do recommend it, because it's one which really fundamentally identifies spatial understanding, 3D understanding is not just something that's, slightly important for you, but it underlies all of intelligence. She talks about how understanding shape and sketching in space is how we reason about the entire world. And if we don't know how to do that, we can't solve anything. In fact, sketching is so fundamental that we use it everywhere. We use it to deform maps to make it easier for us to understand and move between different locations. We use shapes and sizes and spatial orientations to build Legos, or later on as adults now,
All right, welcome back to this morning session on the workshop on autonomous driving. I'm very happy to announce next speaker, Laura Leal Taishi. Laura is a senior research manager at nvidia, where she leads the communication and value group. From 2018 until 2022, she was a tenure-track professor at TU, and she obtained her PhD from the Leipzig University of Hanover in Germany. She is a recipient of the Sofia Kowalewska Award in 2017, the Google Faculty Award in 2021, and the ERC Starting Grant in 2022. Please join me in welcoming Laura.
We organize complex concepts into areas that allow us to visualize and understand them very easily. We create blueprints to understand and build things.
I'm going to apologize because I don't have much of a voice, so I hope it's still understandable. Okay, so today I want to talk a little bit about generative models for 3D data, and in particular, since we are the AV workshop, we're going to talk about LiDAR data, and especially how can we repurpose already trained image models to generate also these very different 3D data. So